presentation, we hear about how we contribute cryptographic functionality to open source stacks. So welcome, Tin and Benjamin.
Welcome from my side. So we're going to talk today about how we introduce elliptic curve cryptography in the open62451 OPC UA stack. And we'll start with a short introduction.
Hello everybody, my name is Tin. I'm a junior research scientist in Siemens in foundational technologies, cybersecurity and trust, and I work in a research group, Security for Embedded Systems. We are kind of an internal consulting service in cybersecurity for other parts of Siemens, and that's how I got to work with Benjamin.
And I'm Benjamin Schilling. I'm a Global Product Lifecycle Manager for Secure Operating Systems at Siemens Mobility. So this talk will not only be about how we contribute elliptic curve cryptography, but also about why we actually need it in railway infrastructure. And we will come to that in a minute. But first, we will have a very brief look at what OPC UA is actually about. So OPC UA is a machine-to-machine communication protocol for industrial automation. It features different architectures. The most common one, I would say, is the client-server architecture, where you have an OPC UA server that provides some values, and you have a client that connects to that server and gets some information from it. For today, we will be focusing mainly on the communication stack, because that's where we contributed parts to. And it's built like this, that you have a transport layer that's typically based on TCP/IP. Then there is some OPC UA specific TCP layer on top of it for a connection protocol. For security, there are various options. The most common one is the UA Secure Conversation. There is a version based on HTTPS or TLS, and also WebSocket Secure Conversation can be used. On the application layer, there is HTTPS, SOAP, or OPC UA Secure Conversation. And for encoding, different versions exist for binary, JSON, or XML encoding. In general, there is only one profile that's most prominently used across all the industries, and that's this one, because that is the smallest common denominator that you have to support in an OPC UA server to be compliant to any profile that they specify. So that's based on TCP, UA-TCP Secure Conversation, and the binary encoding. And most stacks that you can find in the public are also only supporting this protocol or this communication stack. Very few of the other parts are actually supported. And when we now look at why are we using an industrial automation control protocol in the railway industry, it all starts with ULINX. ULINX is a group of European railway operators that started with the goal to standardize the communication between interlocking systems at the trackside of a railway installation, interlocking system and object controllers, which are the devices that control points, signals, all the different parts that we install beside the track where the train is going, and doing this on a European level. And they decided they want to use OPC UA for two use cases. One is diagnostics and the other is maintenance. And they created interface specifications for these, and they are called SDI for diagnostics and SMI for the maintenance part, which also includes software update or engineering data update and all of these things. And from there, there were not many definitions of how the security should be done. OPC UA traditionally supports only RSA. And when we look into the future, of course, you want to have something that also works on smaller devices so that you don't always have to put there much processing power. And from this ULINX standardization, an additional set of standard was created, then also together with the manufacturers like Siemens Mobility, and that's Europe's rail joint undertaking. And that is the big standardization group defining the future of how European railway will work. And in there is a system pillar group and with a working group on cybersecurity, and they just released this first version of cybersecurity specifications. And in there, additional use cases for OPC UA were defined, and also how OPC UA should be secured and what kinds of certificates or keys we want to use there. And that's basically where the elliptic curve cryptography was introduced. Also, new use cases came, like backup and restore and security maintenance, in addition to the ones defined by ULinks already. And of course, we build railway systems. Whatever we build lives for up to 30 years or maybe even longer in the field. We want to have this based on public standards, like, for example, us contributing to IETF with creating RFCs for the part that we need to fulfill these things. But most importantly, and that's what it is about today, of course, contributing to open source software, by this having a solid foundation that we can use to build products upon for the next 30 to 40 years. And this is basically what we will focus on today, and where Tin is giving more insights on what we actually did there and how we achieved to get elliptic curve cryptography into OPC UA for the first time in a stack that can actually be used on embedded systems.
Thank you. So Benjamin covered the big picture and why. I will try to do the how part. So we will focus on the communication layer, as Benjamin showed before, where we have the secure channel, and on the application layer, where we have this session establishment. So secure channel is a secure communication tunnel between a client and the server, and all the messages that go through it are somehow protected. How are they protected depends on the security mode. For none, well, we have no protection at all. For sign, we have we provide the integrity of messages, so we are digitally signing the messages. Sign and encrypt does the digital signature and the encryption. Which cryptographic mechanisms or algorithms we use depends on the security policy that is used for secure channel. As Benjamin said, most of the security policies were based on RSA. ECC was added in the standard additionally. And since ECC is not directly used for asymmetrical encryption, there are some workarounds that need to be done in the code. Now let's look at how we open a secure channel. So we have a client and the server. This is a RSA policy-based opening of a secure channel. We have the open secure channel message. Client sends request, server returns the response. How it works, a client generates a random number called nonce and protects it, encrypts it with server's public key. It also signs the message and includes its own certificate. It sends that to the server. Server decrypts the message, saves the client nonce, generates its own nonce, or also encrypts it, signs the message, includes the certificate, and returns the response to the client. Now they both have both nonces, one from themselves and one from the other party. They use these nonces in a key derivation function, and the output of a key derivation function is a symmetric key or symmetric keys that are then used in the secure channel. With ECC, it's a bit different. We cannot use a nonce because we cannot asymmetrically encrypt it. Therefore, if we send it in plain text, someone might hear it and our secure channel is compromised and, well, not secure, right? So what we do, both client and server, they create an ephemeral or temporary key pair, and then they exchange the public part without protection. The name says it's a public key, so there is no need to protect it. And then each party, of course, they also sign the message and include the certificate. Now each party has their own private key, their own public key, and the other party's public key. All that is sufficient first to perform the elliptic curve Diffie-Hellman, a key exchange protocol. So they obtained a shared secret, same number on both sides, known only to them. And they use this shared secret and also the public keys as a salts, as an input to this time a bit different key derivation function, out of which we again get a symmetric key that is used in secure channel. This is a short overview of open62451. So it's an open source C implementation, reference implementation of OPC UA, around 300 contributors and 4 core maintainers. Here you see the architecture. What is highlighted in red is what's interesting to us and the stuff that we touch. So We have some stuff in the core stack implementation handling the secure channel. Then we have the server and the client SDK that kind of are server and client feature sets, and then the plugins integrate these SDKs into a full application depending on what you need. So we have access control, information model, historical data. For us, the most interesting one is the crypto part with OpenSSL and embedded TLS as the underlying crypto providers. We used the OpenSSL. What we implemented for secure channels, so 2 security policies, elliptic curve, of course, NIST P256 and NIST P384. For sessions, this is a specific for OPC UA standard, so it's not sufficient to only do the protection on the communication layer of secure channel. For session authentication, namely for username and password authentication on the application layer, we need additional protection. So we are not allowed to send the password in the plain text. I mean, it is allowed, but it is not smart, of course. Yeah, so there are also, since we cannot do asymmetrical encryption with ECC, there were also some workarounds needed there to make this possible, this protection of the password with ECC security policies. This is a makeshift bootleg class UML diagram of a part of open62451 that's interesting for us. What's circled in red is what we touched or what was important for us. So we have the client connect and the server session service modules. They are they are implementing the high-level logic for establishing the communication between the server and the client, so both secure channel and the sessions. For secure channel, they use the secure channel module. This secure channel module for crypto operations in secure channel uses secure channel crypto module. And all the security functions, they all go through a security policy interface. It's a well-defined interface with clearly defined functions that each security policy needs to implement. And that's what you see on the bottom left. We have the NIST P256 policy, then we have the NIST P384 policy, and in the middle we have it's called security policy common module, basically some common functionalities that are shared between multiple policies like Diffie-Hellman, this key derivation function, generation of this nonces, and so on. The current state and next steps. So the NIST P256 is merged, NIST P384 merge request is in progress. There are some problems with the test that should be resolved on the maintainer side, hopefully. The interoperability tests were done with a commercial stack, the Softing, and another open source stack in .NET. There were some discrepancies in the symmetric key derivation, some problem. Okay, it was not a discrepancy, it was a bug made by me. I wanted to sound fancy, but yeah, I made a mistake. But we fixed that. It should be now good, yeah. And the session establishment, the implementation is done, but it is for now local because we are in contact with the maintainers regarding some of the architectural and design decisions. Yeah, that would be all. Thank you.
So that's not all of the fancy things that happened. I think we have more stories to tell also at the bar, if anyone has a question on it. Remember, suddenly in the tests, I think there was something with elliptic curve cryptography, that's the P384 being considered more secure than the RSA policies that are actually implemented, and the test cases all failed
it's
suddenly
funny
that they had as regression tests. So.
Yeah, it's funny because the OPC UA defines the security level not by some number, but just descriptive by words like high security level, very high security level, extremely high security level. And they decided to just, from the open62451, they said, okay, high security level, that's 10. Very high is 20, and then extremely high, I think it's 30 or something like that. And there is some problem with tests because this 384 has the highest security level, and therefore they didn't consider it when they wrote tests. So kind of now you cannot test with this policy because the client can't choose a security policy with that high security level. Yeah.
Thank you very, very much.